I'm going to start with this problem where it says p of x is equal to this fifth degree polynomial, and I want to check if x minus 5 is a factor. I know if I divide by x minus 5 and I get 0, that means that x minus 5 is a factor. But we're going to divide using synthetic division since that's a heck of a lot faster than our previous form. So I'm going to put 5 in the little pocket because we always put the opposite of the number. Then I'm going to go 1, got to put 0 down because we don't have an x to the fourth term, negative 24, 4, negative 5, and 2. And then I'm going to bring the 1 down, and 5 times 1 is 5, plus 0, and then 25, and plus is 1. 1 times 5 is 5, and I get 9, and 45, and 40, and they bring that little down, and then 5 times 40 is 200. And I get 202, and that's my remainder. So no, x minus 5 was not a factor. Now it says to confirm by checking p of 5. It says, okay, I don't know what it wants me to confirm, but let's plug it in. That's what p of 5 means. It means I want to do 5 to the 5th power. Well, 5 to the 5th power is 3125 minus 24 times 125, because that's 5 to the 3rd power, plus 4 times 25 minus 5 times 5 plus 2. It's a lot of math to try to do in your head, but let's do it the best we can. This is 3125 minus 25 times 125 is 3125, so this would just be 3100 plus 100 minus 25 plus 2. Well, if I do that entire thing out, I'm going to get, let's see, 3100, 25. Oops. There we go. I noticed I did wrong. This is actually 3000, not 3125. So this ends up being 202. What do you notice? We should notice is that these are the same number. And if your mind's like, what does that mean? That's what this whole lesson's about. This is we notice that p of 5 is equal to the remainder when I divide by x minus 5. This is what the remainder theorem says. If p of x is a polynomial, then for any number c, what does that mean? This is kind of funny. It means that the polynomial is equal to a quotient times x minus c plus this. Okay, so what does this mean? Literally, I know this is kind of what you want to know what this means. What this means is that, in layman's terms, to find p of a number, we simply divide by x minus c and look at the remainder. Okay. This means literally if I wanted to plug any number into a polynomial, the easier thing might actually be to divide by that. Notice how quickly I was able to do this and get the 202 compared with how painstaking this was. I even made a mistake while doing it just because I was trying to do it all in my head. But the biggest operations I had to do in this version were not that big. So here's what it means. It says use synthetic division to find p of negative 5. It wants you to plug negative 5 in. But it wants you to do it not by plugging negative 5 in. This is really wickedly weird, but it's actually really awesome. We can call this synthetic division. We can also call it synthetic substitution. And this kind of remainder theorem, when you understand why it works, and when I get back I'll kind of walk through it a little bit more, but when you understand why it works, it's immensely powerful. So what I'm going to do is if p of negative 5, if I wanted to find that, I'm just going to divide it by x plus 5. Yes, I'm going to take this whole polynomial and put it over x plus 5 and divide. But I'm going to do that with synthetic division, so literally I'm going to steal that negative 5, put it in the pocket, and do 1, 2, negative 1, 4, and set my synthetic division up like we did previously. Then do it. 1 times negative 5, add, negative 3, multiply, 15, add, 14, and multiply, and I get negative 70, and add, and I get negative 66. This means p of negative 55 is equal to negative 66, and that is a heck of a lot quicker than trying to plug it into the original thing. It is. Trust me on this one. Wasn't that quicker? Now, what if the remainder is 0? What does that mean? What does it mean about that? It means two things. It means that whatever we were dividing by is a factor. We know that. That's what remainder 0 means. It means that if you divide by it and you get a remainder 0, it's a factor. That's the factor theorem. P of x has x minus r as a factor if and only if r is a root. So this kind of idea now, x minus r is a factor, and that means that r is a root, are interchangeable, and we're going to use these interchangeably. So moving back up here, what we were dividing by is a factor. That means that if this had come out to be a remainder 0, that would have meant that this was a root and this was a factor. Moving back, this is not only a way to check if a number is a root, you can also check for factors. So if I want to say is x minus 2 a factor, that means is 2 a root? That's really what we're checking. They mean the same thing. X minus 2 a factor means 2 is a root. So what we're going to do is we're going to synthetically divide by 2. 1, negative 4, 5, 4, negative 12. By the way, please note that this is just like these problems on homework. I am trying to help you here. Okay, 2 times 1, negative 2, negative 4, 1, 2, 6, positive 12, and 0. And I can answer confidently, yes. We have shown it with the remainder 0 that yes, x minus 2 is a factor. Let's check it with this one. I'm going to put 2 in the pocket. 1, negative 5, negative 38, 132, and 360. Okay, set it up. And 1, 2, negative 3, negative 6, negative 44. Oh, we're going to kind of large here. Negative 88. This is going to be 44. And 2, and no. I don't even put a number there. It's just no. No, it's not a factor. We didn't get a remainder 0. Ooh, i's. Don't freak out here. We can do the same thing. So if x minus 6i is a factor, that means that 6i is a root. So I'm going to plug that into the pocket, and 1, 34, 36, negative 72. Set up my synthetic division with my little remainder box here, and 1, 6i. Okay, now we got to do 1 plus 6i. And now we're going to multiply 6i times 1 plus 6i. If I do 6i times 1 plus 6i, I get 6i plus 36i squared, which is negative 36 plus 6i. So then I got negative 36 plus 6i. This isn't that bad because if I add, I just get negative 2 plus 6i. Well, when I multiply 6i by 6i, I get negative 36 again. And when I multiply 6i by negative 2, I get negative 12i. And I add, and I get negative 12i again. Or not again, but I just the negative 36 and 36 drop out. And then when I multiply 6 times negative 12, I get negative 72, but I times I is I squared. This is positive 72 and 0. Yes. 6i, oops, not 6i is a root. X minus 6i is a factor. Having fun yet? I am. Okay, so like numbers 17 through 20, this can help solve equations. It is asking me to solve this given that this is already one of the answers. If you remember from the first days of this, I told you that this power here tells you how many solutions you can expect. It's called the fundamental theorem of algebra. So what I'm going to do is I'm going to basically take this and I'm going to divide it by x minus a third. But I'm going to do that with synthetic division. So I'm going to put 1/3 in the pocket, and I'm going to go 3, negative 1, negative 27, and 9. And then I'm going to bring that down, and I get 3. 1/3 times 3 is 1, 0. 1/3 times 0 is 0. Negative 27. and I get 9 and negative 9 and then 0. We're going to take this and we're going to rewrite it as what the term should be. This is actually a 3x squared minus 27, and I know it's a 3x squared because it's 1 degree less than what we started with. Remember, we divided by x minus a third. And my place markers are, this is the remainder, this is the constant, this is the linear term, and this is the quadratic term. So basically that means that this is the no x, this is the x, this is the x squared, and so on. So I'm going to take that and I'm going to set this equal to 0 because I want to find the other two roots. And if I do that, I just basically get x squared is equal to 9, which means that x is equal to positive and negative 3. So it says solve. I need to put all three solutions down, including the one that was given, and that is my solution set. There's 3 solutions for a third degree polynomial. I can solve this one given that negative 4 is a root. So what I'm going to do is we're going to divide by negative 4, 1, 9, 16, negative 36, and negative 80. And when I do that and set this up, I get negative 4, 5, negative 20, negative 4, positive 16, negative 20, positive 80, and 0. It's always good when you get 0 if it says that it's a root. Okay, we got this thing left over, and I want to write that as a polynomial. That would be an x to the third. I know it's an x to the third because it came from an x to the fourth, and our result is always 1 degree less, plus 5x squared minus 4x minus 20 equals 0. You had a question like this on a review packet for a previous test. This is a factor by grouping. Don't do 3 and 1 because there's no perfect squares. It's not a perfect square trinomial. I'm going to take an x squared out, and I get x plus 5. Then a negative 4 out, and I get x plus 5. And if I continue factoring, I get x plus 5 times x squared minus 4. And I have x plus 5 times x minus 2 times x plus 2. In its final factored form. So taking all these different possibilities, I know that I'm going to state the original one first, negative 4, but then I'm going to, from this one, say negative 5, and then these two I can say plus or minus 2. And those are all the solutions of this thing. And there are 4 solutions for a 4th degree polynomial. Okay. Numbers 21 through 28, you only have to do a few of those, but they all have the same direction set. It says find a polynomial equation with integral coefficients that has the given numbers as roots. So I want to find this. Now, you could do it like this, x minus 9, x plus 2, x minus 4. That's fine. We're going to go a little bit faster, and I'm going to pick 2 of them, like these 2 maybe, and just do some product on them. I know that if I do x squared minus the sum, which is 7, so minus 7x, plus the product, which is negative 18, so minus 18. And then I'm just going to take this one and make that the x minus 4. So that let me speed it up a little bit. But I still need to take and multiply and take them and multiply, so I get x cubed minus 7x squared minus 18x. And then I'm going to multiply by the 4. I get 4x squared minus 28x. Minus, let's see, 4 times 18 is 3672, and I get x cubed minus 3x squared minus 46x minus 72, and that's a final polynomial. Now here for number 8, I'm going to really want to do some product on those so I can get rid of the i's. So I'm just going to write this out. Sum is 8 and product is 16 minus I squared, which is 17. So that polynomial is x squared minus 8x plus 17. And I'm going to take it and multiply it by an x minus 3. And if I do that, I'm going to get, let me multiply the x in, x cubed minus 8x squared plus 17x. And then multiply the negative 3 in, negative 3x squared plus 24x minus 51. Add, and I get x cubed minus 11x squared plus 41x minus 51. This next one is like numbers 29 and 30. See, really trying to make this easy on you guys. Two roots are given. Solve the equation. Okay, so two roots are given. Just pick one. Pick the 4 first. Don't worry, we'll get to the 5 here. I'm going to divide by x minus 4. I'm going to do that with synthetic division. So 1, 2, negative 51, negative 32, and 560. And I'm going to bring that down, and I got 1, 4, 6, 24, negative 27, negative 108, negative 140, negative 560, and 0. Okay. This right here represents a depressed polynomial. That's a name that it's kind of a funny name, but it's a name. It's depressed by 1 degree. It's called a depressed poly. And what I'm now going to do is I'm now going to take these and make these the coefficients of my second round of division. I've already taken out, oops, sorry, I need to scroll back down. I've already taken out the 4. So I don't want to take the 4 out again. Why are you down there? What I want to do is take out now the 5. So I'm going to take those and make that a synthetic division with the 5 and set that up. Now, I'm showing it like this because I'm just trying to make you understand later that we actually did this as a separate step. I have the depressed polynomial here, and I'm going to use that to generate the second round of this. Because now I've already taken out a number, and I want to take out another number, but I don't want to write everything out again. So later I'll show you how you can kind of do this in one step without rewriting all the coefficients. 5, 11, 55, negative 28, 5 times negative 28, positive 28 is 140 and 0. Okay, now we're going to take these coefficients and make them back into a polynomial. It's an x squared. If I read right to left, I can see that. Or think about this was an x to the 4th, so that means this one right here is an x to the 3rd, which means this one right here is an x squared. Every time we take a number out, we're decreasing the degree of the polynomial. This should be easy to factor. X plus 7 and x plus 4 equals 0. So my final answer is going to include the 4, the 5, the negative 7 from here, and the negative 4 from here, which you can also state as plus or minus 4 if you want to, or you can just put that. Number 10 says that show that r is a double root. I'm actually not going to read the rest of the directions. You can, it says by verifying that x minus r is a factor of both p of x and p of x divided by x minus r. It's just basically saying divide twice. Kind of like we did up above. This one's like numbers 33 and 34 in the homework. So I'm going to divide this by the 5, and I got 1, negative 7, negative 3, positive 55, and positive 50. Okay. So I get 1, 5, negative 2, negative 10, negative 13, negative 65, negative 10, negative 50, and 0. Okay, now I'm going to change colors to show this thing, but I don't want to have to rewrite this or recopy it like I spent time doing up above. I'm just going to now take the 5 and do it again on this set. And I'm going to stop right there and ignore this 0 here, because now I'm kind of shrinking everything down a little bit. We've already taken a 5 out, so I'm taking it out again. 1, 5, positive 3, positive 15, positive 2, I messed my negatives up, and positive 10, and 0. So now I end up with x squared plus 3x plus 2 equals 0, which does factor into x plus 2 and x plus 3. So it says show that it's a double root. I don't even need to do that. All I needed to do was this. This right here would be enough. I could put like a QED, which is Latin for quod erat demonstratum, or thus it is shown. But it's enough to show this work. This is my work to show that it's a double root. Does that make sense? The question didn't ask me to go any further. I did that automatically, but I shouldn't have, because that's not what the question was asking for. Okay, number 11. How many times is 6 a root? This basically means divide by 6 until you can't divide anymore. So this is a little bit of a game, a 5th degree polynomial. These numbers are going to be a little big at the start, but they're going to get smaller. So we just kind of have to work with them. And I'm going to do this by hand to show you can. So let's set this up. 1, 6, negative 11, negative 66, positive 4, 24, 276. Okay, now I got to do 276 times 6. Let's see, 42, 45, 12, and 16. So that's 1656. Subtract, and I get negative 720. Okay, then multiply 6 by 720, negative 720. Guess what? You get negative 4320. And that's a remainder of 0. So that's 1. Let's do it again. Dot, dot, dot. Bring that down. 1, 6, negative 5, negative 30, negative 26. We have to do 26 times 6, which is 156. So this is actually negative 156. And I get positive 120, positive 720, and 0. Okay, let's keep going. 6. Remember, it's asking us to show how many times, so we're on round 3. 1, 6, 1, 6, negative 20, negative 120, and 0. Okay, we're going to keep going. We're going to go until we can't do it anymore. 1, 6, 7, 42, and done. It did not work that time. We did not get a remainder 0. So 3 times, and I can say 6 is a triple root, because we were able to synthetically divide it out 3 times before we couldn't do it anymore. Now, I could take this and try to figure out, based back on here, what would the solutions actually have been. This is a worthwhile thing, so if I were rewriting these notes, I'd probably say, now let's take this and figure out, okay, so x squared plus x minus 20 equals 0. How could I figure that out? Well, I could have factored it. Or I could do the quadratic formula if it's not going to work out. So remember, the question didn't ask us to do that. This is what we wanted, but I do want you to see that you can do that. Okay, we're done.